Assalamualaikum and a very good morning, everyone. How are you today? We are here in our second topic, still in subject instrumental analysis. Our second topic is about the analysis of samples using ultraviolet visible spectrometry. Ultraviolet visible spectrometry. Okay. Okay. At the end of this course, at the end of this topic in this course, you will learn about what is UV visible, what makes it absorb analyte, the instrumentation, okay, and then we will go into application. Okay, so we will start with the theory of UV visible. This part I will go quite quickly because we already covered a lot of examples of UV visible spectrophotometry in my first topic, which is the introduction of spectrophotometry. I love using this because it is the easiest to make you understand the whole spectroscopy thing. Okay, the analysis of organic or inorganic analyte. This is the instrument that have the capability to analyze both organic and inorganic analytes because it is a molecular spectroscopy. Means that it is a spectroscopy that can analyze chemical compounds. Okay, it analyzes chemical compounds. It doesn't analyze atoms. It doesn't analyze atoms or ions. Therefore, we call it as molecular spectroscopy. That justify why it can do both organic or inorganic analysis. We will go and understand what kind of interaction, absorption, what kind of interaction for organic that makes it enable to be absorbed. Okay, first before that, UV visible spectrophotometry is an absorption spectroscopy. Before this, we covered that we have absorption one, and then we have emission. Okay, this UV-VIS falls under the category of absorption. So these are the few brands available in the world right now, and the most popular UV visible spectrophotometer is Perkin-Elmer. I'm not promoting or anything, but basically Perkin-Elmer is used largely in laboratories, in services lab, as well as in IPT. Okay, and we do have last time we used Shimadzu, and then we also have Agilent, but lastly we choose Perkin-Elmer due to the stability and so on. Okay, as you can see over here, this UV visible spectrophotometry is like the size of a computer bench, and we also have smaller instrument. Okay, it depends on what are the spec inside the UV-VIS spectrometer, just like how you buy car lah. If you want to buy more spec, then the price is higher. In this case, UV visible, when you have more spec, means that it is bigger in size because it want to accommodate those things that is additional. Okay, refresh the electromagnetic radiation as opposed to the wavelength. Ni wavelength ni wavelength ni. And then we we learn that the ultraviolet is having higher energy as compared to the visible. Sini UV, sini visible. While for infrared is having even lower energy as compared to both of these. Okay, the lower the energy means that the wavelength is lower in value. Okay, as compared to infrared, dia tinggi sikit kan. So ultraviolet basically we cannot see. The only spectrum that we can see are in the region of visible. That's why the name is visible, because we visibly can see 7 colors of the rainbow. Okay, ultraviolet UV, okay, the wavelength okay, is between 180, tulis dalam nota you, 180 to 390 nanometer. You see the color I give to you is, it's actually colorless, but I cannot show you colorless, if not you cannot see, right? So it's colorless, 180, and moving towards becoming more violety. Okay, over here 390 is actually really faint color of violet. Okay, so this is the region of UV. Okay, and then move forward, we have the region of visible. So visible, you have a region between 395 to 730 nanometer. Okay, when you see this wavelength, you know already, okay, I actually can see color. Why you see color? Because remember, the sun is giving you the radiation, and the atmosphere filter out the certain wavelength for you to see the colors. Okay, 395, we start with a violety color, violet, purplish over here, and then it goes bluish, and then light blue, and then you go green, yellow, and red. Now you are you can understand the whole thing of when I say purple chemical solution will have lower wavelength as compared to red colored solution. Now you understand it because of this electromagnetic radiation region for all of that. Okay, I will show you the video of the inner part of the UV visible spectrometer. See this video first, and then we can discuss on what's inside it one by one.
Ultraviolet visible spectrometry tells us about electronic transitions in atoms and molecules. Spectra are produced when electrons in molecules or atoms move from one electronic energy level to another of higher energy. In doing so, they absorb energy equal to the gap between the two levels. Compounds that absorb in the visible region, such as some transition metal compounds and organic dyes, are coloured. Those that absorb only in the ultraviolet region are colourless. Inside a UV visible spectrometer, there are usually two light sources, one giving out visible light and one ultraviolet. This one is a tungsten lamp, like a car headlamp bulb, for the visible region. And this deuterium lamp gives out ultraviolet. This mirror directs light from the appropriate source into the monochromator. This contains a diffraction grating that acts rather like the plane surface of a CD to split the light into its constituent wavelengths. Different wavelengths correspond to different colours. Red is about 700 nanometers and blue around 400 nanometers. Wavelengths shorter than about 350 nanometers are called ultraviolet. Shorter wavelength light has higher energy. The source produces white light that includes all wavelengths, all colours. The instrument scans through the spectrum, sending different wavelengths of light through the sample in sequence. This is done by the grating, which rotates. A single wavelength passes into the modulator, which consists of a rotor with mirrors on it. This chops the light into two beams. One beam passes through the sample cell, while the other passes through the reference cell. So the instrument is referred to as a double beam instrument. Both sample and reference beams are directed by mirrors onto a detector. This compares their intensities and sends a signal proportional to the ratio of their intensities to the computer that controls the instrument. The logarithm of this ratio gives a quantity called absorbance. which is a measure of how much light is being absorbed by the sample at that particular wavelength. Ultraviolet visible spectra are usually run on solutions. Light does not normally pass through solid samples. Here, we will run the spectrum of a green food dye. To run the spectrum, we place some of the solvent in a sample cuvette to act as a blank, a reference. The cuvette may be made of glass or plastic if only the visible region of the spectrum is required. Quartz cuvettes are needed for work in the ultraviolet range because glass and plastics absorb UV light. We then place a solution of the sample in a second cuvette. The blank and the sample are placed in the sample holders. The lid is closed to prevent light from the laboratory interfering with the spectrum. The operator types details, such as the wavelength range required and scanning speed, into the computer that controls the instrument. He also zeroes the instrument at a point where the sample does not absorb and then starts the scan. The spectrum appears on screen. The data is saved on the computer and a hard copy can be printed. The horizontal axis is normally wavelength, and the vertical one, absorbance, which is a measure of the amount of light absorbed by the sample. The peaks on the spectrum are the wavelengths of light that are absorbed by the sample, and the troughs are where light passes through. So the dye absorbs orange and blue light and lets through green, so it appears green in colour.
Okay, the video was from the University of Warwick, okay, a few years ago. It's part of the module. Okay, now Go to the next slide. Okay, before that, I just want to summarize, okay, what have been told inside the video. Okay, I want to stress on the final statement from the lady inside the video. Okay, the green solution give us the green color because it absorbs yellow and orange. Okay, that's how it works here. Okay, relate back to the VIS law. Absorbance, okay, when the sample absorb the radiation, in this case it absorb orange and yellow, it will transmit whatever left. Okay, remember my statement before, whatever left. So in this case it will transmit green. That's why our eye can see green solution inside this video. The same thing in other chemical solution. If let's say you see for example purple, it absorbs something. Okay, what something? You can refer to the color wheel that is available everywhere in the internet. Is even learned inside the syllabus in physics. I think last time it is the wheel of the color whereby it absorbs something and it will transmit the color that we can see. Okay, so over here, so this is the visible spectrum. Okay, so when you see violet means that the wavelength selected for the white radiation is around 400 to 420 nanometer. Okay, kat sini. Sorry, Allah Akbar. Okay, I cannot go back because this slide recording doesn't allow me to do that. However, we come to the almost similar slide. Okay, this UV-VIS region. Okay, this is the wheel of color that I mentioned just now. Okay. Okay, violet is between 400 and 420 nanometer, and means that violet is having higher energy as compared to red. Red is relatively lower energy. Sebab apa? Wavelength dia higher. And it is inversely proportional to energy. Okay, red, the UV visible region for red is 620 to 780. Sometimes it stops at 730 actually. Okay. So when white light passes through or is reflected by a colored substance, a characteristic portion, ni yang cakap tadi, they absorb something, they transmit something else, is recorded. Okay, the remaining light will then be assumed as the complementary color to the wavelength absorbed. Okay, and then if let's say you see color yellow, okay, if you see the solution is yellow color, it means that is transmitting yellow while the absorbed colors are violet and dark bluish over here. Okay, the same thing for something else lah. UV visible spectroscopy is used mainly to measure the amount of material in a sample. This is the scope in our instrumental class. Okay. Okay, but does it mean something else cannot be done? No. We can also do qualitative analysis using the spectrum. Tadi ada nampak one spectrum over here. And then kat sini dia keluar grid around greenish to 520 something, right? So this is absorbance. So from here we know that, oh, this is a green colored solution. What kind of green color? It can be apple juice, it can be chromium, or it can be any green dye. And we can determine it by analyzing with against the standard solution. But most of us will do the measurement of the amount. Okay. And this is related to analytical chemistry scope. But what if during PSM later, okay, or when you work later, you are in inorganic analysis or inorganic panel, you can still use UV-VIS spectroscopy to obtain information about atomic and molecular energy level. Remember our Jablonski diagram that we discussed before? You can use this, and then we can understand the chemical bonding. Okay, chemical bonding is very prevalent in UV-VIS spectroscopy discussion, because we can that's where we understand why in the first place the chemical compound absorb UV or visible radiation. Okay, we will go to that part, and then we can understand the interaction of molecules. Okay, interaction dia macam mana, anti-bonding, bonding macam mana. Okay, molecular geometry as well. But this one need extended UV visible learning, which is not covered in this scope lah. Okay, type of UV visible transition. Okay, mostly the most popular one is between pi to pi star over here. Okay, you learn about it in basic chemistry. It is between the when you have a double bond or triple bond, this is where the pi, and then you learn about conjugation. This is where it is used mostly. And then what if you don't have double bond or triple bond? Yes, you still can have UV visible transition is between N to pi star over here, non-bonding to anti-bonding, or you can have sigma, okay, and then jump up into sigma star or the anti-bonding. Okay, the energy between the sigma to sigma star is the highest among all. Absorbing species means absorbing of UV visible, okay, species containing sigma, pi, and an electron. So this is the basic chemistry once again. So the pi is usually denoted by the X over here to show that it is at least a double bond, and then you have a pair of lone electrons denoted by the N. Okay, if you have pi orbital, and then when you have anti-bonding pi star, you have something like this, pi, and then you have this like a butterfly shape over here, anti-bonding. Okay, okay, so let us see if we have here pi to anti-bonding pi. We have unsaturated compound. Usually these unsaturated compounds will give you the highest epsilon. Do you still remember what is epsilon? This one, Beer-Lambert's law. My statement before, the higher the epsilon, the higher the adsorbent. Therefore, the higher the concentration. So unsaturated compounds contain at least one double bond or triple bond. And then we have N, and it can goes up to the anti-bonding of sigma star, whereby it identified to O and S or halogens, okay, for organometallic. Okay, and then we have a carbonyl and to pi star over here, carbonyl, and then we have alkanes. Alkanes means single je lah, sorry, single je. So this is sigma to sigma star. You see the energy is really high. So okay, pi to so for those applicable in our spectrophotometer, basically most of it from this part, pi to pi star, N to pi star. You see that the region is between what we learned just now, between 180 to 730 kan nanometer. This is the range of UV-VIS. Means that lower than that or higher than that, it is actually quite difficult for the detector to detect the transmitted radiation. Okay, and also sigma to sigma star is requiring very high energy to be like excited, to be into excited state. So that's why here vacuum UV less than 100 nanometer is not under the scope of the UV visible spectrophotometer that much. Okay, even though the epsilon is really high. Okay. And then back to this, pi to pi star will give you epsilon between 10 to 10,000. Okay, and then we also have n to pi star. You see over here, this is starting to have visible region. Nampak 400 ke 700. Yang ni UV region. Okay, you can understand now. Those having double bond or several double bond usually absorb around this region. Okay. I also N2 sigma star transition. Okay, is between ni, nampak ni tadi macam vacuum, still very high energy needed Okay, but I don't want to focus on this. I focus on the next one. Okay, N to pi star or pi to pi star transition. You see, this is the lambda max, lambda wavelength, epsilon, and the type of the interaction. Okay. Okay, this is pi to pi star, and then you see we have at least one, and then we have at least one of the triple bond alkyne. Okay, the lambda max is more than 10,000 and above, more than 10,000. Okay, and then we have n to sigma star. Okay, and then we have n to pi. Okay. You see the wavelength is also increasing, right? Just now I said n to pi star is usually around between 400 to 700. Okay, increasing means you are it indicates that the existence of the alkene or alkyne is not there. Okay, see, there's nothing here, nothing here. But we do have this C double bond O in the carboxylic acid part, and then we have this double bond in the N double bond N azo part, and the lambda max is decreasing. This is to show that if you want to analyze a chemical compound, an organic chemical compound, you have to see whether the organic chemical compound contain at least C double bond C, so that you can see the adsorbance easily, because the max epsilon is very high. Okay, the question is that, but what makes a substance absorb UV-VIS radiation? From the discussion about the pi to pi star over here, and then we have n to n pi star. Okay, you can quickly identify, okay, the double bond or triple bond that makes it able to be absorbing the UV and visible radiation. So sini ada double bond, and you see that they are conjugating. Okay, conjugation help the compound to absorb more radiation. Okay, when you absorb more radiation, means that the molar absorptivity or the epsilon is higher. Okay, chromophore is the unsaturated organic functional group. Okay, chromophore is very largely identified as the component responsible for absorption. Okay, while for inorganic compound, we will discuss it later. So this is for organic compound only. Okay, but if you have organometallic compound, itu cerita lain. Okay, because it have a hybrid. Now focus only on the organic compound. Okay, organic chromophore is the organic functional groups that give you the ability to excite, to enable the excitation when the radiation comes in from the lower energy ground to the higher energy level. And when you have conjugation, it will help you to absorb to a longer wavelength. Maksudnya, kalau you mula-mula absorb at 420, if you have conjugation, maybe it will move or shift betochromic towards 450. Okay, because of the conjugation. Kalau contoh you ada macam ni lah. Okay. Okay. Molar absorptivity may be very large for strongly absorbing chromophore, more than 10,000, and it is very small if the absorption is very weak. The magnitude of epsilon reflects the size of the chromophore, and also the probability that the light of the given wavelength will be absorbed when it strikes the chromophore. Okay, this is the example of the chromophore. Chromophore, once again, is a functional group. Okay, organic functional group. C double bond C and C triple bond C will have a higher epsilon. Okay. Lambda max is usually around 180 to 171. This is more towards a lower visible UV region. But if you have conjugation, remember, kalau you ada conjugation like this, okay, it will shift from 171 to maybe 190, and then lagi banyak lagi 205, and then maybe 210, and so on. Okay, and then we have carbonyl. Okay, there, and then we have carbonyl over here. It can be very high epsilon when it is at vacuum UV, but once it shifts towards longer wavelength, the epsilon reduce. Okay, so if a compound only contain the carbonyl without any C double bond C or C triple bond C, you will see a very small peak inside UV visible spectrum. Okay, usually a compound contain both this one, or this one, and the nitro part. Okay, same thing from here. Higher wavelength will have lower epsilon. Okay. These are some example of natural organic pigments. You can predict how big the value of the epsilon is, because it contain conjugation. Then it contain the carbonyl, okay, and also it contain oxochrome. Okay, apakah oxochrome? I will cover later. Okay. Beta carotene even have a higher conjugation. Okay. So you will see. That's why you see carrot with like orange color. Okay. Absorption type, okay, we covered for organic compound, whereby it contain the chromophore, and usually it can chromophore such as C double bond C, C double bond C triple bond C, and then you have carbon and so on. Okay, but what if you are analyzing inorganic species? So inorganic species, okay, they can absorb broad bands of visible radiation in at least one of their oxidation state. When you see chromium, you usually nampak macam hijau-hijau, yellow-yellow sikit kan. Sometimes ada sikit blue. And then when you see nickel or zinc, sometimes bluish, right? Okay, the absorption is between filled and empty d orbital. Okay, when you see d orbital over here, it reminds you to your first year subject with inorganic chemistry. You learn about transition metals. Okay, I don't want to go into this part so much, but transition metals are those metals that is in periodic table, that is having d orbitals part Okay, and usually it is colored and contain at least oxidation state number 2 or oxidation state number 3. So you can go and Google up, and the first two transition series, such as the chromium, the manganese, okay, and so on, it can absorb it UV visible region. Okay, what if you have inorganic species and you want to complex it with organic compound? This is where you have the organometallic. Yang tadi cakap agak complicated tu, organometallic. So this is what we call as charge transfer absorption. Bila you dah masukkan organic compound inside the metallic inorganic species, you will have a lot of higher number of epsilon number, because it contain electron donor group, okay, and means that the electron pair from the donor is transferred to the acceptor orbital. For example, iron 3 complex can be complexed with 110 phenanthroline, producing red color. Okay. Okay, so this is an example. The example again, this is on the conjugation. So when you conjugate, you will have some most of it will shift to the longer wavelength. That's where we call as spectrochromic shift. Some of it will give you higher absorbance. Sometimes it will reduce the absorbance more than that. If you go to lower wavelength, you will have hypsochromic. If the shift is towards a higher absorbance, hyperchromic, and lower absorbance as hypochromic. Okay, this is the oxochrome. The group of atom attached to a chromophore which modify the ability. Okay, oxochrome per se, tadi ada satu oxochrome OH kan? Oxochrome bersendirian will not absorb UV visible radiation. But when it, for example, kalau ada OH, this is not possible, tapi just for the sake of showing you, if it has OH over here, it will help this conjugated benzene ring over here to have even higher epsilon. This is usually used in the making of cloth, dyed cloth. There's sometimes some of them manufacturer, they purposely put alkaline salt inside the whole dye system so that the dye color intensity is even higher. It does not absorb UV, but it help. That's why nama dia oxo. Oxo datang daripada perkataan auxiliary. Okay. So do you think cyclohexane absorb UV-VIS radiation as strong as benzene? Adakah ini akan absorb sama seperti benzene? Jawapan dia no lah, sebab there's no C double bond C and there's no conjugation at all. So cyclohexane will not absorb radiation as compared to the benzene. The types of UV-VIS spectroscopy, we have photometer and spectrophotometer. Both having the same principle, but the difference is that the component in the filtering of radiation. Photometer is a simple instrument that use filter. Dia cuma guna filter je to select wavelength. And when it comes to filter, it can only detect single wavelength at one time. Therefore, this is not versatile and cannot generate entire spectra. But does this mean photometer is not useful at all? It doesn't mean that. Means that the photometer is only suitable for routine analysis. Siapa-siapa nanti later when you work in a QC/QA department, sometimes they only want to analyze one thing. So they bought photometer, and this is even cheaper as compared to spectrophotometer that can do everything. Okay, so in this case, you as a chemist later, okay, if you are asked by your boss to select, okay, which one should I use or which one should I buy, you have to understand the whole thing and able to explain to your superior or colleague on which one to use according to your cost and also throughput. Throughput means berapa banyak analysis you nak buat. Okay, for example, over here we have very famous portable spectrometer whereby it only have filter. Kalau you nak analyze yellow, dia ada filter dia. Lepas tu if you have a red color, you buka filter yellow, masukkan filter red. Okay, example Spectrophotometer, in the other hand, it contain monochromator ataupun we call it as dispersive element to scan various wavelength. Like source putih kan? Okay, diffract means that if you ask this grater to only select 420 and it will only select terbalik. Okay, betul. It will only select 420 to go into the monochromator. Ni this is aperture. Sepatutnya kena ada satu entry slit over here. Okay, this is called as monochromator. Because it has more components, it is more expensive and more flexible. Means it can analyze a lot of wavelength. Banyak wavelength boleh analyze. This is usually used in R&D industries. Okay. Okay, we have a sourcer, wavelength selector, is it filter, is it monochromator, we have a sample, cuvette, detector and so on. Okay, I will go very quickly because we will do active learning on this instrumentation. Okay, so I will stop the video of class now. We will have active learning. Okay, after we take a break after this, we will have active learning on cooperative learning, bukan e-learning, sorry cooperative learning, whereby we will use Coggle Up. Apakah Coggle Up ini? So Coggle Up ini basically is a very modern name for mahjong paper. Okay, we will do mind mapping real time online with 45 of us for 30 minutes on. Okay, on the topic of instrumentation in UV-VIS spectrophotometry. So form 9 groups, 5 students in a group. Macam mana nak tahu 5 student? I put over here 1 to 5 group 1, 6 to 10 group 2 and so on So you go into the Coggle, I will give you the link for each of you. Okay, I will give group 1 to 9 and you brainstorm or you put essential information. Jangan ambil pada nota I because we want to proliferate the information. Okay, means that tambah information lagi in the Coggle. Okay, so with that